Hi, I'm Gok Yu Hui. I'm going to present my final year project entitled Model Predictive Control of Pump Kernel Shell Gasification for Maximum Energy Generation. In this presentation, I will cover introduction, problem statement, objective and scope, methodology, result and discussion, and finally conclusion. Due to the rapid growth of technological development and population, the electricity consumption and demand in Malaysia have been increasing dramatically every year. However, Malaysia is highly dependent on non-renewable energy sources, such as natural gas to produce electricity. So, waste-to-energy become a potential technology. Every day, people are generating waste. The biomass generated from agriculture sector is 168 million tons annually. This is due to Malaysia is one of the biggest producer of palm oil. 5.64 million hectares of oil palm planted areas nationwide at the end of 2015, which is equal to about 23% of Malaysia's total land area. 1 hectare of oil palm plantation can produce about 50 to 70 tons of biomass residues. Hence, there is a huge amount of biomass which generated from palm oil industry. Of the total output from the oil palm tree, about 10% is palm oil, while 90% is in the form of oil palm biomass, which has yet to be fully exploited. The biomass that we are going to discuss in this study is palm kernel shell. Among the oil palm solid biomass, palm kernel shell contain the highest calorific value and the lowest moisture content. The main factor influencing the production of energy through biomass gasification are the calorific value and the moisture content of the feedstock used. The efficiency of fuel or food mainly depends on the calorific value. If the value is high, its efficiency will also be high. Whereas moisture content also affect the energy for drying. Low moisture content increase the efficiency of process by reducing the energy consumption in the drying process. Thus, palm kernel shell gasification with combined heat and power system is an emerging technology to solve environmental problems such as greenhouse gases caused by increasing energy demand, together with depletion of the fossil fuel. However, the major problem of this biomass gasification with combined heat and power system is its bulkiness and inconvenient form of biomass, along with the complex multivariable system with multi-load. So, we have to develop a control system to optimize the process. In most of the study that carried out by the other researchers, proportional integral differential PID controller is used to control the power output, but this type of controller method does not meet a satisfied result during dynamic state and gasification process. Thus, multi-predictive control (MPC) has been developed to control the power output. This is to reduce the reliance on the experimental approaches and to have a financially and environmentally desirable bioenergy outcome at optimal condition. So the main objective of this study is to analyze the behavioral performance or sensitivity analysis of palm kernel shell gasification with combined heat and power system, and to evaluate the control performance of palm kernel shell gasification with combined heat and power system at its maximum power output, which is 20 kW. But what is model predictive control? Model predictive control uses current dynamic states of the process variable targets and limits to calculate the future changes in the independent variable. The forecasting is achieved using the process model. Thus, a dynamic model is essential while implementing model predictive control. This implies model predictive control is an iterative, predictive, feedback-based control strategy. This is the comparison of two controller strategies, PID and MPC, where PID controller uses the current and past states of the system to adjust the actuator. For an example, where the orange car drives too near to the left-hand side of the road, the system only will correct it and adjust it back more to the right-hand side. While in the MPC, it follows the model and the present measured value. If the model is good, it follows the set point value. For an example, the green car, it will just drive according to the accurate path. However, a small error in the model can lead the system astray, like the orange car and the blue car. Moving to the next part, methodology. The flow of the simulation is started by developing a steady-state model of pump kernel shell gasification with combined heat and power system in Aspen. Then, a dynamic state model is built from the steady-state model. From these sets of data, we generate an empirical model in MATLAB. From this, we design an MPC controller using MATLAB toolbox. So my scope of work is starting from developing a dynamic state pump kernel shell gasification flowsheet by using Aspen plus dynamic software. From here, we will get a set of data including flow rate, temperature, pressure, and power. Dynamic model is used instead of steady state model because dynamic state model runs in real time and is able to mimic the behavior of the real process, which cannot be done in the steady state. The system boundary of the process is as shown, where it is divided into 4 parts. 3 sets of 720-hour simulation is run. The dynamic data of each input and output is then exported into MATLAB. From the dataset, an empirical model which describes this process is developed by using System Identification Toolbox. In this System Identification Toolbox, the Aspen dynamic data is imported as MyData. Then, the data was segregated into 2 subsets, one for model validation and one for model estimation. Nonlinear autoregressive with exogenous input NLARX model are selected to be estimated. After the validation process, the model with best fit percentage at 5 steps ahead prediction output with 95% confidence level were exported to the Simulink workspace. This model will then undergo open-loop dynamic analysis to investigate the process behavior of the pump kernel shell gasification process with combined heat and power process when dealing with process uncertainty, such as set point changes and disturbance. This is the model that used to carry out open-loop dynamic analysis in Simulink. The step change were introduced one at a time during the simulation and have been altered independently, where one input is varied and the other remain constant. This is the model validation result for the 10 outputs of the system that undergo using System Identification Toolbox. As we can see, the orange line represents the NLRX model, while the black line represents the Aspen dynamic data that we imported. The model underpredicts the value for output Y2 and Y3, and slightly overpredict for the Y4 output. Overall, the model and all the experimental outputs matches well. We can conclude that all the model outputs have above 85% best fit and is feasible for use. Lastly, a MPC control system was designed and developed, and the control performance of this process is evaluated. This is the MPC control design. The control objective of the system is to control the power output at its maximum, which is 20 kW, while the manipulated variable is the mass flow rate of the syngas. As we can see at this part, this is the step changes that apply to the system, while this is the manipulated variable, which is connected into the input of the plant model, while the output of the plant model is connected to the measured output. The control performance can be read from the scope. For the result of open-loop dynamic analysis, the variation of oxygen mass flow rate typically associated with the change in the plant. The power output increases when subject to the positive step change. Another experiment that undergo is determine the effect of syngas mass flow rate. It will observe that for a negative step change, the power output increases. By comparing both of the experiment, we can say that syngas mass flow rate has a faster response than the oxygen mass flow rate. When applying the same step time, syngas mass flow rate are significant to the power output and thus selected to be the manipulated variable. By designing the MPC controller, it was found that the best control and prediction horizon of this control system is set to be 2 seconds and 10 seconds respectively. The control analysis is conducted as Simulink environment based on the set point trajectories 15th, 18th, 12th, 15th, and 20 kW using Model Predictive Controller MPC. From this figure, It was found that the MPC has ramped up the gasifier power output to the required demand whenever the set point changes. MPC model took around 18 minutes to respond to the changes while the overshoot in this model is less than 1%. The oscillation times are small as well. The model able to reach and stabilize the set point around 24 minutes, and the root mean square error of this model is 14.14, which is very small. As a conclusion, a dynamic modeling is built based on the steady-state model in Aspen Dynamics. From this set of dynamic data, an empirical model describes the pump kernel shell gasification with combined heat and power process is developed and validated in Simulink via System Identification Toolbox. For open-loop dynamic analysis, step changes were introduced to the input variables independently, and the model results appear reasonable. Model predictive control schemes were studied. This control scheme is aimed to control the power output of pump kernel shell gasification with combined heat and power. The simulation results have shown that MPC able to reach and stabilize at the desired output, which is 20 kW, without significant overshoot and damping. This is due to MPC can eliminate the control error faster when stabilizing to its set point. Thus, all the objectives in this study has fulfilled. That's all for my presentation. Thank you for listening.